My name is Mark Yaksh, and I'm here to present the final presentation for Team 1A, the White Wizards. My classmates were Ryan Johnson and Sam Palmieri. First, the function tree. We needed to win this competition. That was our overall goal. We needed to open gate, and also in this open the gate, we needed to also lift it and hold it. We also needed the thing to be safe. To retrieve the pin, we were going to do this by extending after and then move the pin. Claim the center object. We were going to extend an arm and move the objects, which would have been the ring and Arkenstone. And lastly, displace a squash ball, which would be into a 6-inch round PVC pipe. The next critical design tool was the house of quality. Here we compare the customer needs to the engineering requirements. The takeaway from this slide, though, is that the number of actuators, seen here in this column, and the lifting height of the gate were going to be very critical for us in the designing of our robot. For our final design build was it. It has 5 subsystems. The lifting system to lift the gate, the platform system to extend everything out toward the center of the track, the drop system to drop the squash ball, the lasso system to retrieve the pin, and the lever R system to retrieve the ring or the Arkenstone. The first system we will talk about is the lifting system. Now this uses a 4-bar lift system. Now what this allows is that as the lifting pads go from the ground all the way to its max height of 20 inches, they will stay completely level, allowing no binding of the gate to occur. Now the way this lifting action happens is that a rod is knocked out of the way here, then causing the counterweights to fall down as seen by this arrow, thus lifting up the lifting pad in this direction. The next system is the platform system. Now this was activated that as the 4-bar linkage came up here, it knocked this holding rod out of the way, allowing the counterweight to fall through a series of pulleys with strings. When this happened, this propelled this platform forward at an accelerated rate. And this was done by riding on 2 18-inch drawer sliders. The next subsystem is the drop system. Now this uses an 18 drawer slider which is extended by its own momentum. Then the metal pin will hit the PVC pipe, which will rotate it out this holding arm. Thus the squash ball will drop through the hole and into the PVC pipe. Next system is the lasso system. Now this system uses a 14-inch drawer slider which extends out from its own momentum. On the bottom of this platform is 2 3/4-inch nuts which fall down this dowel. And this is done by once the string is taut, the pins pull out and allowing it to fall. Then a motor mounted to the main plate will pull the pin back home. The last system is the lever arm system. Now the way this device works is that as this device is propelled out through a pneumatic piston, this 22-inch drawer slider will pass this holding plate. Once it passes this holding plate, this lever arm here will swing around this axis of the mouse trap, extending it all the way out. The very tip of this lever arm will touch the side of the drum, and as the opening of the drum comes around, it will swing in toward the ring and knocking it into our zone. Here we have the design build fully deployed. As you can see, the weights are dropped, everything is extended, and the holding rod, which was sitting up here, is now down here resting on the plastic platform. Now here we have the bill of materials. Now the key thing to take away from this slide is that the drawer sliders, the 18, the 22, and the 14 were the majority of our costs, followed by the oak board, which was used mainly for all the supports, which for a grand total for us was $71.88, which is far below the $100 limit. The first alternative design is design filling. Now this uses 2 lifting arms which are connected to these 2 pneumatic pistons. Now when these pistons are activated, they will lift the gate. Then this platform sits on these 2 guide rails which are inclined. And what will happen is that solenoid will trigger, cause this platform to slide forward toward the pin. Now, on the bottom of this platform is a mouse trap. This mouse trap will hit the top of the pin and knock it back toward home base. Then, through gravity, this robotic claw will slide out and grab the arc and stone and the one ring. Our next alternative design is dolman. Now, this uses, again, two lifting arms, but is offset by a counterweight. Now, as this counterweight falls, the lifting arms will lift the gate. Then, these drawer slides, which are four, two of them holding this basket crane. This basket crane will go over to the PVC side and then rotate and drop the ball into it, while this robotic claw reaches out and grabs the one ring and arc and stone. Lastly, this mousetrap here, mounted on the bottom of this claw, as it passes over the pin, will hit the top of the pin and knock it back toward home base. The last alternative design is design Golan. Now, this uses a worm gear drive to rotate these lifting parts up to the top, lifting the gate. Then, using these scissors arms, will extend out, the first one being the robotic claw, to grab the top of the piston and bring it back. Then, this hook arm, which will reach out and grab the one ring or arc and stone. Lastly, using the air tank and compressed air, we will shoot the squash ball through the air and into the PVC pipe. Now, the highest level evaluation we used for this project was the third level evaluation matrix. Here, we compare the criteria from the function tree and the importance by the customer. Now, the important thing to take from this slide is that what really made Bilbo the best design is placing the squash ball and the low cost. Now, the low cost could be seen in the building materials. For the final cost for us was $71.88. Now for the competition results. In the first round, we scored 0 points, but still placed third. In the second round, we scored 25 points and placed second. In the third round, we scored 0 points and placed fourth. For the competition results for each of the rounds, the first round, what happened was the position was in the wrong place. Also, the motor did not rotate. So what we did is we took it aside after the round, repositioned the position to the right location, freed up the motor by taking it out and turning it by hand. And the second round, the squash ball was placed and the gate was open, but the lasso system did not grab the pin. This is because the string was binding. Thus, we took the string off the motor and unwound it, and then releasing the binding of it. In the third round, unfortunately, the piston problem came back and it moved. We didn't knock the support out, thus we did not open the gate or place the squash ball. We did reline the pin after this incident, but we were already knocked out of the competition by then. In summary, Design Bilbo was meant to score 48 points consistently every round. However, due to unforeseen issues, we were not able to accomplish that. Now, to fix these issues, it was decided by the team that a better brace for the pneumatic piston would have fixed the issue of it moving. Thus, we would have knocked the support out every time and getting the gate in the squash ball. Next, the lever arm system to retrieve the one ring and arc and stone should have been two 14-inch drawer sliders, which would have put us much closer to the center turret. And we could use a small lever arm system, which would have greatly reduced the chances of not setting off the IR sensor and receiving dice. Also, to more consistently grab the pin, a third holding point for the lasso should have been included. This would have stopped the chance of the lasso system slightly missing the piston. Overall, the White Wizards were very satisfied with the design.